Hello guys, and welcome to another lecture in the Energy System Analysis Python course. My name is Anas Abuzayed, and in today's video, we'll talk about Numpy. So what exactly is Numpy? Numpy stands for Numerical Python. It's a library that you can import in Python, and it supports large and multi-dimensional arrays with a lot of mathematical functions that you can apply on. So what exactly is NumPy? We learned previously that we have lists, we have different arrays, let's say in Python, like lists, sets, tuples, and dictionaries. So what's the difference between NumPy arrays or NumPy as a library and the built-in arrays from Python itself? So NumPy itself requires less space, so less memory space compared to other arrays. And there is a lot of flexibility, a lot of functions that you can use, mathematical functions, as in summations or means or average or standard deviation and so on. So statistical functions or trigonometric functions like the sinusoidal or cosine and so on. So there is a lot of functions, even more on the statistical side. And most importantly, why do we use NumPy arrays? Is because it can have multi-dimensional or more dimensions. So we learned previously, if we want to create a list, you can do it either a list of lists, so you can have somehow quasi multi-dimensional, but mostly it's a singular dimension or 1D. While in NumPy, we can create as many dimensions as we like. So let's say in both, you can, in principle, use them. There is no big difference here. But of course, there is a different syntax, different method of using both. So it's a very useful tool to master. And in the end, if you want to use the built-in arrays of Python itself, or you want to use NumPy, or later on we will learn about pandas, in principle, there is no big difference. So let's say commonly we create lists, let's say, or create a built-in array from Python itself and then convert it somehow to NumPy array. Why do we do this? It's, let's say, most commonly that's how we do it. It's a bit efficient. And we will later in this video learn that it's somehow difficult to append or to add new elements to arrays in NumPy. So let's start from the beginning. How can we import it? So it's a library that is built in, let's say, in Anaconda, in Conda, and you can import it and use it. So if we use the function import and then we say NumPy, it's basically now imported. So if you say in NumPy, it's a module that is found here. So let's say ideally or commonly, people you will find always when you search anything for NumPy that people do it like this. Sorry, NumPy as NP. So if you import it as NP, this basically means instead of writing NumPy as a whole, you just say NP. So it's the same. Here, it doesn't really mean anything. So you can import it as an X or as Y or let's say as O. It doesn't really make any difference. Let's start with the very basic array. So how can we create one? Is simply by this. So NP array, and we need to create something in here. So let's say an array of one element. So here you can see that it's one array, one element. So this is a zero dimensional, like the ones we had previously in the built-in arrays in Python. The difference here is that we can have 2D or 3D or also 1D or 0D. We can have 100 dimensions. So there's no difficulties in that. Of course, it will be difficult to manage them, to know how to manipulate them, to access them, but in principle, it's possible. So if we say np.arrange, and then we say 1 and 2, oh, sorry, array, not arrange, then now we have an array that has 2 dimensions. So if we say it like this, we can even create a 3D array, something like this. Would look like this. Let's say the first bracket is for the first dimension, and then we open another one that's for the second one, and then a third one. So let's just put like this. One. just to make it a bit easier. So here is the third dimension. So we can say, for example, 1 and 2, and then let's say 3 and 4. So this one here is for this dimension. And then we say, so something like this. Array. So it might look a bit complicated now, but we will go through it exactly how it looks like. So let's say now we have this array. Let's just say A equals this one. So how can we exactly access it? First, we need to know how many dimensions are there. So ndim will give you the dimension. So it has 3 dimensions. Now, if we want to say a dot shape, then this gives us basically the shape of it. So let's say we want to access this one here. So how can we exactly access it? As we did previously with the lists, so we can just open brackets and then access it. So a of 0 would give us the first element, a of 1 would give us the second one. So we want to say we want to access this one, which is in the second one, so a of 1. And then again, we want to access the first element. So the first list, the first dimension of it. And then we want this 4 again. So this would be again 0. So this is our 4, this one. In Numpy, we can use it in a different way by saying a 0 and 0. So instead of using brackets or different ones, we can do the same also here. Let's add more components to it. So let's say 3, 4, 3, 4, 5, 6. So let's add this one. And as we did previously with the selection inside the list or inside a tuple, we can also do the same here. So if we want those 3 numbers, so 4, 5, and 6, we need to do it like this. So a of 0 would give us the first one, and then we need to go to the second dimension, or the second, but in Python it's the first. And then we need 4, 5, and 6. So from 1. So the same thing that we did before. Let's say we want the last 2, so 8 and 9. How can we do it? Is by accessing the second one, and then again the second one, and then -2, something like this. So that should be, I think, easy. It's the same that we did before. Now, if we want to create an array with a number of dimensions, so let's say array 1. So this would give us a 0 dimension array with no dimensions. So if we say, let's say a equals this one, and then a dot n, so it has 0 dimensions. So let's say we want to create different dimensions here. So we use ndmin, not ndim, and then you can create an array of 9 dimensions. Of course, if your application needs 9 dimensions, then you can easily create it with Numpy. So we learned about how to slice it. Let's try to change it. So we copy this one again here. So we know how to access it. Let's see how we can change it. So now we have A, which is a 3-dimension array, and we want to change this number here. Instead of 6, I want to say, let's just put 6.5 there. So how can I access it? It's in the second element. So first, and then, sorry, the first one, and then 0, 1, 2, it's the third one. So if I say this equals 6.2, and then I run it, if I check now A, it will not be executed. And the reason for that is because of the data type. So if I say a dot d type, then it gives me that this array, the data type in there is integer. So unless we define it as float, it is by default an integer. So that's why when we executed this one, 6.2, and then if we check it, it's still an integer, not a float. So how can I do it? Is by using as type. So if I say float here, now we can see it executed. But is A already a float? No. So that's why we need to say A equals A dot as type float. So define A as a float. Define the data in A as a float. Now we have it as a float. So if we execute this one again and then say A, now we see that it is changed. So it's very important to know what exactly is the type of data you're dealing with. We can also use the same, let's say, and as a Boolean. So again, there's no 0 and 1 here, so it will all be true. Let's say we change this one initially and make it just 0. So now A has those numbers and has 0 here. So if I say A as a Boolean or as type Boolean, then we see that this one here turns out to be false. So we learned previously that if we want a list of numbers, let's say from 0 to 12, including 12, we can do it with list range 13. That will give us from 0 to 12. If we want it from 1 to 12, it's 113, then we get it. In Numpy, there is also another function, so that's arrange. If you do the same, 13 np.arrange, it will give you an array with the components from 0 to 12. So it's the same as range before. If we do it like this, it's 1 to 12 or 1 to 13, not including 13 or excluding 13. We can also do it with a jump, so something like this. So it's the same. Now, let's see, here we have an array. So np.array, let's say b equals this one. Now, b is an array of shape, so it's one dimension, and the shape is 12. So b in the im is 1, and the shape is 12. So it has one dimension with 12 elements in it. So we can reshape it inside Numpy to have different types, or let's say different shapes, different matrices inside. So it's a very useful tool by saying b.shape and then inserting your shape. So here you can, for example, let's say b itself has, you can understand it as 12 columns, one array, 12 columns. So instead of 12, 1, you can say 112. Reshape, we have B that has one row, 12 columns. And then we can reshape it by having 12 rows and one column, something like this. Or we can have, for example, so here, mind that if we do not say B equals B dot reshape, the original shape will stay the same. So unless you assign it, or unless you say, okay, this is the new value or this is the new shape, the original one will stay the same. So you can say also, let's say 12 values here, we can say 3 times 4. So 3 rows, 4 columns. Now the shape of this one is 3 by 4 and in dimension, so it's a 2-dimension. We can even make it, let's say 3-dimension by saying 3, 2, and 2. So it will have 3 dimensions and then 2 columns for each. So it's basically a 3D matrix. We can, I think there is lots of variations that we can do here. The most important is that we do not exceed 12 elements. So let's say if we say 6 by 2, this would give us 6 rows, 2 columns. But if we say 6, 2, and 2, it cannot reshape an array with size of 12 into a new shape, which is 6, 2, and 2. So think about what kind of shapes you can create, or you can reshape your array based on the numbers that you have in the original one. So let's say now this one here, let's take the 3D one. So let's say C equals this. So we define a new array, C, that is 3D and has, let's say, 3 elements, 3 dimensions. So C of 0, the first dimension is this one. And let's say we want to access the 4, so this would be C1 and 1. So let's see how can we iterate over it if we want to iterate over the elements. So go inside each dimension and print all of them. So if we say for X and C, and then print X, this would give us the inside count. So I want the numbers, the actual numbers to be printed out. So I want to access each one of them. So here we come to the idea of a nested for loop. So now X itself is an array. So I need to access it. So I need to iterate over it. So let's say for Z and X, and then again, print Z. Let's see if this would give us the numbers. So now each time I go, I find a new array that I want to access again. So we do another nested loop. So it's 3 for loops inside each other that you want to access. So for, let's say, Y and Z, yeah, that's awkward. Let's say like X, Y, and Z. So now if we say print Z, this would actually give us the whole numbers. So to access all of them, or let's say to access them one by another. Why? Because it is a multi-dimensional array. So in order to access it, the first time you access the first dimension, then the second one, and then the third one. The third one is actually the numbers. So this array, C, has 3 dimensions. Each time you do a for loop, you access one of those dimensions. So until you want to reach, or if you want to reach the actual numbers, the last dimension, then you need to do nested for loops until you reach that last dimension. So let's say we talked previously about having more dimensions. So is this really very practical in case you have lots of dimensions? So let's say A is non-dimensional here. So if we want to access it with a for loop, it will take us 9 for loops just to access the last element, let's say the last dimension. So there is another function here that we can use that accesses them. So inside the for loop, it accesses the last dimension of it. So if we try it on C, that function is x in n numpy dot this one with this, and then print x. What it basically makes is that it accesses the last dimension and prints all of them. So if we do it on this one, and then let's do the same. Instead of having 9 for loops, here it's not C, it's A, it will access the last dimension. So in this case, it's 1. So this is a very useful tool in case you have lots of dimensions or in case you don't know how many dimensions you will create. So from here, we move to, we talked previously in the let's say the built-in arrays, the Python arrays. How can we append or create a list, or let's say take two lists or 2 keys or add next to each other. So now in NumPy, it's a bit different. So if you see from, let's create a 2-dimensional array. So array 2D, and let's create array 1, that is 1 dimension, and array 2, so the new thing about NumPy arrays that we did not see in the Python arrays is that we have access. So we have columns and rows that we did not have before. So for example, here we can see that it has 4 columns, 1 row. If we go to the next one, the array 2D, you can see that it has 2 rows, 1 column. So in case we want to merge them together or to combine them together, can use a function called concatenate. which basically combines the two NumPy arrays next to each other. So if we say array 1 and array 2, so here we have only one dimension, so only one axis. If we say array 1 dot in the IM, that's one dimension. So if we want to add it, we can only add it on that dimension, on that axis. So concatenate here adds data to the NumPy or combines them only on existing axes, or axes. So it does not create new axes. Let's try it out. So if we say np dot, and then we say array 1, let's just do it A1 and A2 just for ease. So A1 and then A2, and then see the result of that. Wait, start define. So it basically adds new columns. Why? Because we already have an axis, which is the first axis, and it only adds them as new columns. So there is here something called axis. So axis, basically, if you go, that's one tip also. If you say help np dot concatenate, and then you can basically see the documentation of it. So axis here means the axis along which the arrays would be joined. So that's where we have a difficulty here with concatenate, that we cannot add a new axis. And of course, if that's in case of multidimensional, it says if axis is none, then they will be flattened. We will see how or what exactly that means. So if we do it again, then they are just added next to each other. So can we do it, let's say, on top of each other by changing with the axis? So if we say axis 0, that's basically somehow vertical, then they're added next to each other. And if we say axis 1, then it would give us that axis 1 is out of the bound. So it does not have more than one dimension, more than one axis. So let's say we do it with a 2D. So array 2D is this one. And let's say we want to add the two on top of each other. So, or we want to merge them together. So if we want them, let's say this is the first row, the second row, and then let's say this is the third and the fourth row. So if we try it out now, go here, and then this one, and then this one. So the default is axis equals 0. So if we do not want to change the axis, the default is 0. So now it's basically added on axis 0. This means a vertical addition. So it adds on top of them. So adds new rows. If we say axis 1, then it will add a new column. So you see it, let's say, let's just make this a bit bigger. So what's this one, and this one, and then this one, just to compare all of them. So we see that the first one, that's 2DA and 2DB. So that's the two rows, 4 columns, 2 rows, 4 columns. So if we do it on axis 1, it adds horizontally. So it adds new columns to the result. So the resulting array would have a new shape, which is 8 times 2, where this one would be 4 times 4. Why? Because we added it on axis 0. Let's see if we make axis equals none. So we read that if axis is equals none, then it will be flattered. What does this mean? Is that basically we'll turn it into a single dimension or one dimension where all the numbers are just laid next to each other. So now let's go back to the first example that we did. So we have A1 and A2. If we want to add them on top of each other, let's say 2 rows, we said that we say axis is 0. That's basically what we did here. So it adds new rows. But in the single dimension or in the first dimension here, it doesn't make anything. And if you say axis is 1, which is what's the result here, so it will give you an error. And the reason for that is that concatenate only adds on existing axis. So for that, there is another function. If we want to, let's say, put the arrays, so this one, this one and that one, if we want to put them on top of each other or next to each other, there is another function called stack. Stack, what it makes is that it stacks the arrays over each other. If we say np.stack, and then we say a1 and a2. Now, if we try it, and then we say, okay, axis equals 0, it basically adds in a new row. So in order to do that with concatenate, we cannot, but with stack, we can do it. So if it's a singular dimension, because as we said previously, it's only existing axes, while stack can add new axes, but only as a combination. So for example, let's say that's 0, and if we say 1, that's the new column. Let's just show it, all of it together. And then we say this is 0, and this is 1. So if you see it now, when the axis was 0, it added a new row. And when the axis was 1, it added columns. So it made the first one, A1, 1, 2, 3, and 4 as columns. So 4 rows, 1 column. And the second one, 5, 6, 7, and 8, it made a new column with the 4 elements in it. So there is other functions, for example, H stack or V stack or D stack. So it's somehow the same. Of course, here, if we try it before we go there, so if we say, okay, axis 2, can it create a new dimension? No. Why? Because we have two one-dimension arrays. And when you combine them together, you can only get 2 dimensions of it. So 2 axes. And of course, in stack, you cannot have the same as none. So if you also try it, so it's V stack is the same as axis 1. So you already saw it here. That's the H stack. Because we said none, if we do none, you get an error. This one here. So if you do it with H stack, you clutter all of the arrays into 1 dimension. So if we check, for example, the shape and dimension of each one of them, let's say this one. So this one, it's a 2D with a shape of 2, 4. It's not callable. And this one is a 2D and with a shape of 4, 2. And so here it added a new dimension. And this one here would be a singular dimension. So that's why it can be somehow complicated. It can be overwhelming to know where exactly what happens. And let's say in the dimensions, it can be really difficult if you have, let's say, 4D or 5D to know exactly how to stack them over each other or add them to each other or concatenate next to each other. So next we have the append. So in lists, for example, we know that we can append anything to a list or to array or even add a new key to a dictionary and so on. But in NumPy arrays, it's a bit different. So how it looks like is those ones here. And we want to append them. So here you say A1 and A2. So you can, because they are only one dimensional, so in append, in case they were one dimensional, you can only have one axis. So if you say axis equals 0, this will give you the same result. So you can only add them, let's say, if you want to append next to each other. So in case, let's say you have some kind of data acquisition device and you want to divide them as arrays, then you need to add them, let's say if you want to add them on top, so as new rows, then you need to add, or let's say use VStack. But if you want to append them, so let's say axis equals 1, it will give you an error because it's out of the dimension. Now, if we say, or if we go back to the second, the 2 arrays or the 2-dimensional arrays, and we use the same. So this one and this one. So axis 0, it will append them on top of each other. Now, if you see the shape of this one, it's a 4 times 4, where if you say axis 1, and again dot shape, so that's 2 times 8. So if you remember previously, when we added, the shape differs if you do concatenate or stack or append. So it's very important here to note what exactly happened to the new shape so that you know how to deal with it if you want to iterate over it or so on. And let's say in case of 2D, if we do not define the axis. So what will happen is that they will also get flattened. So the shape of this one is singular. So there is some functions here in NumPy that I thought you might benefit from learning. So one of them is rand integer. So if you say something like this, it will give you a random integer each time you run it. So in this case, it's any number lower than 10. So if you say a million, for example, well, that's 10,000, you get always different numbers. So in case you want to have a random, let's say a sample, this would be something interesting to do. Another one, if you want to create a random array. So let's say you want an array of a random shape, random numbers, and so on. So if you say np.random.rand, and then you put a shape here. For example, let's say 100. So let's do it with 10. So you get a random array of the shape 10, and each time you have different numbers. So if you do the same, each time you get different new numbers. So if you say the shape in a different way, 2 times cos, sorry, 2 and 2, so that's a shape of 2 by 2, then you get different ones or different, let's say, arrays with random numbers with a shape of 2 by 2. If you want them, let's say, as integers, so not as decimal points or not as floats, you can use the same one here, the rand integer. So any number below 10,000, and then you say size equals, say, 2 by 2. Then you get a 2 by 2 array with integer values here. So it's, let's say you want to make it even more random. So instead of 2 by 2, you can use the same one here. So this one of 10 and this one of 5. So what will I do here? Each time I run this command, I will have a random array of random shape. Of course, it's 2D, but because I defined it here, but I would not guess what kind of dimension would get there, because any number less than for 10 or any number less than 5. So something like this. So each time you run it, you get a new shape. So for example, here, I got 1 by 0, so nothing. So speaking of ones and zeros, there is another function in NumPy, which is zeros. So here you see it, shape. So if I say shape equals 2 by 2, you get a 2 by 2 array of zeros. If you say it here, D type as bool, so you get it as bool and false. In this case, it's always false. So other functions, for example, let's say if you want to deal with random data and somehow you want to test it or to test a theory on it, is a random choice. So for example, let's say n.random, and then you say choice. So let's say 5 with a shape of 2 and 2. So here we got this error that there is no argument called shape. So just to show you how you can use the function help. So if you say help, it will give you the documentation of it. You can also Google the documentation, you can find it, but here it's more practical. So here you can see that there is, even with examples. So what are the arguments or the parameters that you can use? It's size, not shape. So if you do it like this, it will give you a random choice of numbers with a size of 2 by 2. So the last function that we have in NumPy is the trigonometric functions. So sine or cosine and so on. So let's say the sine of 90. It's not 1 in this case. Why? Because if you go to the definition of sine, it should be in radians, not in degrees. So how to do this is by multiplying it or converting it to radians. So to do that, you need to multiply by 2 pi, so 3.14 over 360, or 1 pi over 180. So if we do this, we don't get 1. We should get exactly 1. So here we have another function, which is n dot pi. So this gives you the exact number of pi. So if we replace this 3.14 by pi, then we get the exact 1. Another tip, for example, instead of each time doing np.pi or np.sine or cosine, you can just import it. So how to import it properly is from numpy import pi as. If we do pi now or pi, this would give us the symbol. So this here, this function, or sorry, this line here, 165, is equivalent to me saying pi equals np dot pi. So either this or that. The same would be import sine as sine. And whatever you change here is up to you. So you can say x. So now x is a function, or sine. But of course here it should be identical with how numpy defines it. So it's defined in numpy as sine. So let's run this one. Now if you go back to this one, instead of np.sine, you can say sine. And instead of np.pi, say pi. So it's the same. The last thing in numpy, which is very important, is something that was defined by the IEEE, by the floating numbers or the floating points standard, which is the NaN, so not a number. Usually when we have bigger data frames, or let's say bigger data entries, there might be some missing values or values that cannot be expressed as a number. So in Python, this is called NaN. So if you want to define an NaN, is either with numpy, or you just say float NaN. Later on, we will take pandas and other libraries like other pandas or math. So this is how you create it. And of course, in there's other ways to create it. So it's a floating point or a floating number or not a number. So how to check if a value is not a number or NaN is very important, because this NaN affects the quality of your data. So you need to replace it. This is the whole idea, let's say, behind the course, is how to deal with data. So it will be very important to know how to identify them. So to check them, there is a function in NumPy. It's called as NaN. So let's say a equals np.num. So a itself, you can see it here, it's a num, or not a number. And then we say np.asNaN, or it's not a number, and then we put the number in there. So our entry, we want to check if this is a nan or not. Let's say b equals 5. And then we do the same on b. So this would give us a false. Here it gives us a true because it is not a number, and for b it's not. The most common one, without using, let's say, any libraries like pandas or numpy, is by saying a equals to a. So if you check this one, and let's say b equals b, so b is not none, so this will give us a true, while a equals a, this would give us a false, even though it's the same, we're comparing the same thing. But here, because it's a floating point or floating number, or not a number actually, such as 0 over 0 or something like this, so it's how things are defined in Python. There's not really much behind it, but it's basically how things are defined in Python, or how NaN is defined in Python. With that, I finished the video for today, and thank you for watching.